Section 4.8, Exponential and Logistic Growth and Decay. The general form for our exponential growth and decay is going to be n of t is equal to n sub naught, or n sub 0, times e to the kt. And if you'll notice, this is the exact same formula as continuously compounded interest. Now you may not believe me, but our formula was a was equal to p times e to the r times t. We're approaching these two things exactly the same way. This n sub 0 is some initial amount, where n of t is how much we get after some amount of time. But now we're just talking about general exponential growth as opposed to strictly talking about money. Other things to note, n sub naught is the initial amount. And for our exponential growth, one of two things is going to happen. If our k is a positive number, then we're going to call it growth. But if k is a negative number, then we're going to call it decay. And realize that depending upon the real-world application, sometimes the things will grow and sometimes the things will decay. Since we're talking about growth and decay, it's possible to refer to doubling time and half-life time. Well, the deal is that what happens is doubling time is the amount of time it takes for some amount to double in size. And what's going to happen is if we take that initial formula that we had, that n of t is equal to n sub naught times e to the kt. The trick here is that if we're talking about doubling time, what we're really doing is we're saying, look, what if I were to take and I were to double that initial population or initial amount that we're concerned about, and then I wanted to know how long would it take for that to occur. Well, if that's the case, then we get this equation. And then if we try to solve that equation, well, you can divide both sides by n naught, divide by n naught, then I get that this is going to be n naught divided by n naught is 1, so I'm left with 2 is equal to e raised to the kt. Then what can we do? We can take the natural log of both sides. Then I get that this is the natural log of 2 is equal to k times t times the natural log of e, but natural log of e is 1. And then because we're looking specifically for either k or t, just divide by the one that's missing, and we get exactly these formulas. T is always going to be equal to the natural log of 2 divided by k, or if you were looking for k, that is the growth rate, that's going to be the natural log of 2 divided by t. Half-life ends up being very similar formulas, but that's because if I were worried about how long does it take for a population to cut in half, that initial setup is 1/2 of the initial population is then equal to n sub naught times e to the kt. Then I would solve for k or t depending upon which one I needed, so you could divide both sides by n naught, and then you're going to get 1/2 is equal to e to the kt. Then take the natural log of both sides, and when you take the natural log of both sides, this looks an awful lot like what we just did. You'll get the natural log of 1/2 is equal to k times t comes out front times natural log of e is 1, and then from there you can get either one of these formulas for the half-life. So as an example, the size p of a certain insect population at time t in days obeys the model p of t is equal to 500 times e to the 0.02 t. Notice that this is exactly that formula that we're looking at, that is n of t is equal to n sub naught times e to the kt. So we are using that formula, they just gave it to us from the get-go. So just some observations. That means that our initial population of insects is 500, and the growth rate, notice that this is positive, is 0.02. So now let's say that we want to determine the number of insects at 0 days. Well, this is just a value. P of 0 is going to be equal to 500 times e to the 0.02 times 0. Well, 0 times 0.02 is 0. E to the 0 power is 1, and so our answer is 500. And look, that's exactly what we said. We said the initial population would be 500 insects. Then we want to know what is the growth rate of the insect population. And so notice that our k in this situation is 0.02. Or if you needed this in a percent format, that's a 2% growth rate. Now if we want to know what is the population after 10 days, we just evaluate p of 10. P of 10 is equal to 500 times e to the 0.02 times 10. That is 500 times e to the 0.2. Then I'm going to approximate, and since we're talking about these insects, I'm going to round to the whole number. And so this is just a choice I'm making. This is 611 insects. Notice that this is the exact same equation, so now we just want to know when will the insect population reach 800. If we know that the output population is 800, that's going to be an equation. 800 is equal to 500 times e to the 0.02 times t. Well, first step, I would divide both sides by 500. I get 8/5 is equal to e to the 0.02 times t. Then I can take the natural log of both sides, and so I get that this is the natural log of 8/5 is equal to the natural log of e to the 0.02t becomes 0.02t times the natural log of e, but remember that the natural log of e is 1, and so then divide both sides by 0.02, and I get that t is approximately 23.5. Now, depending upon our rounding, we may want to round to the whole day, or this is a half day, so in 23.5 days, the insect population will reach 800. When will the insect population double? Two ways to do this. First off, if you want, realize that you could set up the equation knowing that the initial population is 500. That is, you double it, that would be 1,000 is then equal to 500 times e to the 0.02t. And then you could solve this equation. There's no reason necessarily to remember the doubling time and half-life formulas, unless it makes you happy. But on the other hand, if you do all this, what are you going to get? You are going to get that t is equal to the natural log of 2 divided by k, where specifically in our situation k is 0.02. So then our solution will be natural log of 2 divided by 0.02. And so I get the population will double in approximately 34.7 days. A culture of bacteria obeys the exponential law, or the law of uninhibited growth. If n is the number of bacteria in the culture and t is the time in hours, express n as a function of t. This is our exponential growth formula. So that is n of t is equal to n sub naught, that initial population, times e raised to the kt. So now if they say that 500 bacteria are present initially and there are 800 after 1 hour, how many will be present in the culture after 5 hours? Well, this is a multi-step problem. First off, what do we get? We get that if we use this information, 500 bacteria give us that this formula is really 500 times e to the kt. But there's a problem. I don't know my growth rate k. But they tell me explicitly that after 1 hour, there are 800 in the culture. Now, since they say that the time is represented in hours, then it's perfectly fine if you so desire to go 800 is equal to n of 1, because 1 hour, which is really going to be 500 times e raised to the k times 1. Then we have an equation that we can solve for k. So let's solve that. Well, I'm going to divide both sides by 500. Then I get 8/5 is equal to e to the k. Then I'm solving k, so let's take the natural log of both sides. Then I get that this is the natural log of 8/5 is equal to the natural log of e to the k. But remember that the k comes out front, and so this is then the natural log of 8/5 is equal to k times the natural log of e, but the natural log of e is 1, and so the natural log of 8/5 is just equal to k. So we've found the exact value here. But we haven't answered the question, because we want to know how many will be present in the culture after 5 hours. Well, what did we do? Well, we just found our k value. And so if we found our k value, that means that now I really get my complete population growth formula. That is 500 times e to the natural log of 8/5 times t. And so now, if I want to find how many bacteria will be present in the culture after 5 hours, then this is just a formula that we just found. That is, n of 5 is then going to be equal to 500 times e raised to the natural log of 8/5 times t, where t is 5. This is just a calculator value. When you calculate these things, make sure that you put an extra set of parentheses around that product as the power of e. And I get that this is approximately 5,243 bacterium. Notice that we're using the exact same formula we had before. That is, n of t is equal to 500 times e raised to the natural log of 8/5 times t. Well, we want to know what's the time that it's going to take for us to get a population of 20,000 bacteria. So how does this look? We know that the output is 20,000, and that's equal to 500 times e raised to the natural log of 8/5 times t. Then let's divide both sides by 500. We get that this is 40 is equal to e raised to the natural log of 8/5 times t. We need to solve for t, so I'm going to take the natural log of both sides. This is going to look a little strange for a moment, but bear with me. This is then the natural log of 40 is equal to the natural log of e raised to the power of the natural log of 8/5 times t. The natural log of 8/5 times t is a power on e, so it'll come out front. The natural log of 40 is equal to the natural log of 8/5 times t times the natural log of e. But of course the natural log of e is 1, and so then we're left with the natural log of 40 is equal to the natural log of 8/5 times t. We're solving for t, so divide by the natural log of 8/5, and I get that t is approximately 7.8, and our units were hours. Always pay attention because this unit of time can change when we're talking about population. Whatever you've established that time frame in, whether it's hours, days, months, weeks, it carries throughout that problem. And so for this answer, it takes 7.8 hours approximately to get to that population of 20,000 with the specific growth rate. A baseball card sold for $100 in 1971 and was sold again in 2007 for $324. Assume that the growth in the value V of the baseball card has grown exponentially. We see exponential growth. So my first thought is to just write our equation down. That is, n of t is equal to n sub naught times e to the kt. So exponential growth just means this in general. But now I'm going to adjust it for our situation. Well, since we're not talking about growth or the number of people in a population, we're talking about money, or in this situation value, I'm going to change my n's to v's. Alright, so then I have a value over time, and I have an initial value times e to the kt. Okay, great. Alright, so what else can we do? Well, the first thing we're told to do is find the value of k of the exponential growth rate. Well, that makes sense. We need to find k. We also already know that the initial value is 100. So we're going to assume that because it was sold one time, we're going to assume that initial value is $100. And then after some amount of time, the period of time between 1971 to 2007, it sells a second time for $324. Well, what should we do? Well, we need to figure out how much time passed between 1971 and 2007. So 2007 minus 1971, we get a total passing of time of 36 years. And so 36 years, what we're going to say is that V, our formula here, of 36, after 36 years, the amount that it was worth was $324. Well, if we use this, then, knowing that our initial value, V sub naught, is $100, then I get a partial equation, that is 100 times e to the kt. So then, to find the value of k, we know that after 36 years we get 324 being the output. So 324 is equal to 100 times e raised to the k times t. We don't know the growth rate k, but we know that t for $324 was 36. And so k times 36. Then we just need to solve for k, so divide both sides by 100. I get 3.24 is equal to e to the 36k. Then I'm going to take the natural log of both sides. I get that this is the natural log of 3.24 is equal to 36k times the natural log of e, but the natural log of e is of course 1, and so we get that this is the natural log of 3.24 is equal to 36k. I'm solving for k, divide by 36, divide by 36. I get that k, after a rearrangement, is approximately 0.033. Now this is of course an approximation, so watch out. Now if you needed to write that in a percentage form, it is 3.3%, but when we're doing our calculations, remember that we're going to use the decimal form. So now we want to find the exponential growth function in terms of t, where t is the number of years since 1971. And so we were almost there. We now have that v of t is equal to 100 times e to the 0.033 times t. And so there is our exponential function. Now we want to use our formula that we just found. V of t is equal to 100 times e to the 0.033t, and we want to find the answers to these other problems. So if we want to estimate the value of the card in 2011, well, remember that first off, 1971 was our starter year, which means we want to know how many years passed between 1971 and 2011. That is 2011 minus 1971, which is 40 years. So if we want to estimate the value of the card in 2011, that's after a passing of 40 years, so we're going to evaluate v of 40, or 100 times e raised to the 0.033 times 40, and I'm just going to round to the nearest dollar, and that is approximately $374. What is the doubling time for the value of the card? Well, of course you could set up the situation where you double the initial value, which is $200, set it equal to the 100 times e to the 0.033t, or you could have used that memorized formula, that is, doubling time is equal to the natural log of 2 divided by k, which is going to be the natural log of 2 divided by 0.033, and I get that this is approximately 21 years. Now we want to know, after how long will the value of the card be $1,056? Well, the output is 1,056. Set our equation equal to that. That is equal to 100 times e to the 0.033t. Now we just need to solve for t. Divide by 100 on both sides. I get that this is 10.56 is e to the 0.033 times t. Now I'm going to take the natural log of both sides. I get that this is the natural log of 10.56 is equal to 0.033 times t times the natural log of e. Natural log of e is 1, and so then divide by 0.033 on both sides, and I get that t is equal to the natural log of 10.56 divided by 0.033, or approximately 71.4 years. Iodine 131 is a radioactive material that decays according to the function A of t is equal to A sub naught times e to the negative 0.087 t, where A sub 0 is the initial amount present and A is the amount present at time t in days. Assume that a scientist has a sample of 100 grams of iodine 131. When will 70 grams of iodine 131 be left? All right, just for understanding, if you have radioactive materials that decay, that means they stop being whatever material they start out as. And they have some rate of decay because they're unstable. And so if we have this question, well, let's start. Here's our formula. A of t is equal to A sub naught times e to the negative 0.087 t. So the initial amount was 100. So that is our A sub naught. So our equation, A of t is equal to 100 times e to the negative 0.087 times t. And if we want to know when will this be equal to 70 grams, well, we just need to solve for t. So let's divide both sides by 100. We get that e to the negative 0.087 t is equal to 7/10. And then if I want, I can go ahead and take the natural log of both sides. That's then going to be negative 0.087 t times the natural log of e, which is of course 1, which is then equal to the natural log of 7/10, divide by negative 0.087, and I get that t is equal to the natural log of 7/10 divided by negative 0.087, or about 4.1, and our units were days. If we want to know what the half-life is, there's two ways to do this. Realize that if you start with that initial equation that we found, which is a of t is equal to 100 times e to the negative 0.087 t, you could solve the equation for the time when half of this is left. So you could start out and say 50 is equal to 100, that's half of 100, times e to the negative 0.087 t, and then of course you could solve for t in exactly the same way we just did. Or if you're a formula memorizer, that's perfectly fine. You can use the fact that t is going to be equal to the natural log of 1/2 divided by k. We know that k is negative 0.087, and so that's the natural log of 1/2 divided by negative 0.087, or I get that this is approximately 7.96, which becomes 8.0 days. And so that's the half-life. After 80 days, this sample will only include half of its original iodine-131. The half-life of radium is 1,690 years. If 10 grams are present now, how much will be present in 50 years? All right, so we got lots of steps here. First thing is, remind yourself, we have our regular exponential decay formula. A of t is equal to the initial amount times e to the kt. They tell us that the half-life of radium is 1,690 years. So, using the fact that we know half-life, this is actually where the memorization of the formula could be useful. We can find our k, where k is equal to the natural log of 1/2 divided by t. Well, if the half-life is 1690, that is natural log of 1/2 divided by 1,690 years. And for the sake of not making a mistake, I'm going to leave this as is for an exact. And so if the half-life of radium is 1,690 years and 10 grams are present, how much will be present in 50 years? Well, we have our k, so our actual equation is going to be initial amount of 10 times e to the natural log of 1/2 divided by 1,690 times t. So that's all the exponent. Thus, we're calculating a of 50, which is 10 times e to the natural log of 1/2 divided by 1690 times 50. I get that this is approximately 9.797 grams. So that's how much would be left after 50 years. The radioactive element carbon-14 has a half-life of 5,750 years. A scientist determined that the bones from a mastodon had lost 85.9% of their carbon-14. How old were the bones at the time they were discovered? All right, so a few things. First off, if we have a half-life, we need to find a k. And so once again, this is where the formula could be useful. K for half-life is going to be equal to the natural log of 1/2 divided by the time t, which we're told is 5,750. So now we found k. All right, great. Now a couple ways to deal with this percentage. If we're told that they lost 85.9% of their carbon-14, then we can assume that we started with an amount of 100%. And so let's just say that the amount after time t is equal to an initial amount, let's call it 100 for 100%, times e to the k, which is the natural log of 1/2 divided by 5,750 times t. Then since the amount that was lost was 85.9%, the question then becomes how much was there? Well, if they lost 85.9, 100 minus 85.9 is really going to be 14.1% was remaining. So notice that I decided to think of this as 100% was the total initial amount. They lost 85.9% of their carbon-14, which means that they have 14.1% left. Since we want to know how old the bones were at the time they were discovered, at this point we say 14.1, that's how much the amount was left, is equal to the 100 times e, k, that's natural log of a half, divided by 5750, times t, and we can solve for t. So let's divide both sides by 100, divide 100, that is 0.141 is equal to e to the natural log of a half divided by 5750 times t. I'm going to take the natural log of both sides. Then I get that the natural log of 0.141 is equal to the natural log of a half divided by 5,750 times t. I'm just going to put that t right there, times t, times the natural log of e. Well, of course, the natural log of e is 1. And so then I can divide by the natural log of a half over 5,750. Then notice that I have fraction division, which becomes fraction multiplication, which is then 5,750 times the natural log of 0.141 divided by the natural log of a half, which I get to be approximately 16,251 years old. So now we want to fill in this table. But realize that this table is just giving some information relating growth rate to doubling time for the populations of separate countries. So for the US, they tell us that the doubling time is 77 years. So remember that this is where that formula memorization could be useful. K is equal to the natural log of 2 divided by t. On the other hand, when we're talking about doubling time, you could also say that t is equal to the natural log of 2 divided by k. And these formulas are going to be what we use to find both our growth rates and our doubling time. So if we're told that the US doubled its population in about 77 years, then our k is going to be equal to the natural log of 2 divided by 77.0 years. And I get that this is about 0.009, but in percent form, move the decimal place to the right twice, that's going to be 0.9%. So our growth rate is approximately 0.9%. Now given that Australia had a growth rate of 1.11%, first things first, we need to convert that 1.11% to a decimal instead of a percent. And so we're going to use this formula, t is equal to the natural log of 2 divided by k, and that's going to be t is equal to the natural log of 2 divided by 0.0111, or approximately 62.45 years. That's our doubling time. Then for Sweden, we're given the doubling time, so we need to find that growth rate. Well, that's going to be k is equal to the natural log of 2 divided by that 385 years, or approximately 0.0018, which in percentage form is 0.18%. Notice that for this one we're talking about radioactive substances, but now we're talking about half-lives and decay. And so that memorized formula could be useful. That is, k is equal to the natural log of a half divided by t, or alternatively, t is equal to the natural log of a half divided by k. And so then we can take, and we're told that the half-life of lead-210 is 22.3 years. And so then to find that k growth rate, k is going to be equal to the natural log of a half divided by 22.3 years, which is approximately negative 0.0311. Now notice that this is negative because it's decay, and so if you were to put this into the equation a times e to the kt, it would have to be a negative k. But here they're calling it decay, so we're not going to write the negative because it's implied. And so the percentage for our decay rate is going to be 3.11%. Now for iodine 125, if we're told that the decay rate is 1.15% per day, realize that now we're looking for that half-life t. T is then going to be equal to the natural log of a half divided by Now watch out, we've got to change it to a decimal and we need to make it negative. So this is going to be negative 0.0115, which then gives me approximately 60.3, and our units are years. And so our half-life of iodine 125 is approximately 60.3 years. And then we repeat the same thing for krypton 85. So T is going to be equal to the natural log of a half divided by negative 6.5% decay rate, which is going to be 0.065, or approximately 10.7 years.